Hello, this is Matthew Ferrero, and this is my Lab 6 report on the magnetic molasses. The purpose of this lab is to observe Faraday's law and compare how long it takes a magnet to fall through a tube with induced fields. A preview of the results is that the larger the value of the magnetic dipole moment, the more the tube will change in current. Here are the fundamental principles used in this lab. So you have Biot-Savart law, which calculates the magnetic field generated by a specific element of an electric current. It is fundamental in the magnetostatistics for relating current flow to the resulting magnetic field strength and direction. Faraday's law states that a changing magnetic flux through a circuit induces an electromotive force or voltage in that circuit. We also use Newton's second law. In this experiment, the system was the magnet and the foil, and the surroundings were gravity and other surroundings. Here I'll explain the procedure. As you can see on the picture on the right and the explanation for the setup, we dropped a magnet through an aluminum foil tube while recording, and then we use this visual data to track the speed of the magnet falling through the aluminum tube. The length of the tube was 0.45 meters, with the width of the foil being 0.2 meters. The magnet had a mass of 0.37 kilograms, and there was a radius of 0.18 meters, and the average time it took for the magnet to drop through the tube was about 2.3 seconds. So here is a part of the code that we used in GlowScript to simulate this experiment. We can see that I found the dipole B value by finding the magnitude and R hat value and then plugging it into the equation for B. And then on the right side, we see that I manipulated the starter code we were given to insert the values we found previously in the code, all in an effort to plot the graph of velocity versus time for the magnet as it dropped through the tube. And here's the graph we got from GlowScript. We can see that it took a little bit of time for the velocity to get to its constant velocity, but after it does, it remains pretty constant throughout the entire falling through the tube, where then once it exits the tube, it falls off in velocity just a little bit. In conclusion, the simulation had a similar fall time compared to the recorded fall time found in the experiment. Regardless of the direction the magnet fell from, the current induced in the aluminum foil would have been counterclockwise. And some potential sources of errors that could have been found either both in the physical and simulated experiment could have been some potential fluctuations in timing and recording the time it took for the magnet to fall through the tube, and also errors in rounding and precision of calculations, so sig figs, other things like that. And here are the answers to the discussion questions. The first one asks, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So for the magnet to fall at the same time with resistance being zero, there would have been some sort of magnetic influence between the aluminum and the magnet. Next question asks, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? And having any sort of like hole or slit cut into the induced magnetic into the tube would cause the induced magnetic field to decrease.